Artificial intelligence, deep learning, machine learning, whatever you're doing, if you don't understand it, learn it. Because otherwise, you're going to be a dinosaur within 3 years. Wow, okay. That incredibly urgent warning from Mark Cuban, that perfectly sets the stakes for us today, right? We are living in a moment where understanding the actual underlying mechanics of AI isn't just a hobby for software engineers anymore. It's absolutely crucial for, well, anyone who wants to navigate the future without getting left behind.
So, welcome to This Explainer. Our goal today is highly focused, and honestly, I think it's completely transformative. We are going to take AI entirely out of the realm of inexplicable magic, and we're going to ground it firmly in logical mathematics. By the end of our time together, you won't just know what a neural network is, you're going to understand exactly how it learns.
Here's our roadmap for today. We're going to cover the big picture of AI, brains to artificial networks, inside the hidden layers, the mathematics of learning, and finally, from math to reality. Let's get right into it. Section 1. The big picture of AI. Understanding the basics. Okay, so the absolute core takeaway here is that AI, it isn't magic. No way. It is literally just the theory and discipline of programming computer systems to learn from and spot patterns in datasets. That's the whole shebang. Whether it's recognizing speech or making complex decisions, AI is just a system looking for patterns. Once you realize it's all about pattern recognition, man, it clears up a lot of that initial confusion, doesn't it? Now, under this massive umbrella of AI, we have some very specific disciplines. You've got machine learning, which focuses on algorithms predicting trends without human help. Then there's deep learning, which uses complex architectures to process totally unstructured data. We also have natural language processing, or NLP, letting computers understand text and speech, and computer vision, which allows them to interpret images. But, right beneath all that incredibly popular generative AI we use every single day, like ChatGPT, sits the humble engine powering it all, the artificial neural network.
Section 2. Brains to artificial networks. Biological inspiration.
So, check this out. There's this brilliant visual bridge between neuroscience and modern computer science. Way back in 1943, 1943, a neuroscientist named Warren McCutcheon and a logician named Walter Pitts actually discovered that neurons in the human brain perform logical operations. It's fascinating. Just like biological neurons have dendrites receiving signals and synapses connecting them, an artificial neuron basically mimics that. It takes in numerical inputs, applies a mathematical transformation, and passes a signal forward. But you're probably wondering, how does this artificial brain actually learn? Well, it follows a really clear narrative. First up, inputs. Data is gathered and fed into the system. Next is processing, where the AI deciphers that data, desperately looking for patterns. Then we get outcomes. The AI makes a prediction. But crucially, we then get to adjustments. See, when the AI gets it wrong, and it will, it learns from its mistakes by tweaking its internal rules. And finally, assessments. It synthesizes all those insights to make much better predictions the next time around. Section 3. Inside the hidden layers. Network architecture. All right, let's picture the data flowing forward from the left to the right. The entire network is organized into layers of interconnected nodes. Now, those middle layers, the ones totally sandwiched between the start and the finish, those are called the hidden layers. And let me tell you, these hidden layers are where the actual magic happens. This is exactly where the transformations occur and where the network really learns to identify those super complex patterns. It's really helpful to look at the start and the end of this journey. The input layer on the left, it simply receives the raw data. Think of it like pixels in a digital image. And the output layer over on the right produces the final prediction, like confidently outputting the word apple or orange. Now, we just have to demystify what in the world is happening in that hidden middle space. Section 4. The mathematics of learning. The mathematical engine. Brace yourselves, we're diving into the math. When a signal travels from one neuron to the next, it gets multiplied by a parameter called a weight. Think of weights as the artificial equivalent of those biological synapses we talked about earlier. Just as human synaptic links change their strength based on our learning experiences, these mathematical weights are constantly adjusted up or down to strengthen or weaken the connection between specific data points. Okay, so after all the inputs are multiplied by their weights and added together, another parameter is introduced. It's called the bias. Honestly, biases simply give the network some much-needed flexibility. They act kind of like an anchor that can shift the baseline prediction left or right. This just ensures the network can actually fit the true shape of the messy data it's analyzing. Finally, that whole weighted sum plus the bias passes through what's known as an activation function. And here is exactly why this matters so much. Without these activation functions, our super futuristic AI, it could only draw straight, linear lines. That's it. Functions like ReLU or sigmoid introduce nonlinearity. That means they allow the network to twist, to bend, and to accurately model the incredibly complex, messy relationships of the real world.
Let's anchor the math here for a second. The data flowing left to right to guess an answer? That's called forward propagation. But the guess is usually totally wrong at first. To figure out exactly how wrong, the network uses a cost function, most commonly something called the mean squared error. This essentially calculates the exact mathematical distance between the network's prediction and the actual correct target. So, once the network knows its error, it has to fix it, right? It does this through backpropagation and a really clever algorithm called gradient descent. Just imagine the network is standing on the side of a massive 3D valley, and the elevation represents its error. It wants to get to the very bottom where the error is practically zero. Gradient descent is simply the network calculating the slope of that valley and taking incremental, tiny mathematical steps downwards. It slightly adjusts all those weights and biases we talked about until it finally reaches the lowest possible point. Section 5. From Math to Reality, the Future of AI.
Now, this is exactly why you should care about all this math. There's something called the universal approximation theorem. It's a mathematical proof establishing that a neural network with just a single hidden layer can theoretically approximate any continuous function. Period. This demonstrates exactly why neural networks are the ultimate engine for our future. If a relationship exists in the data, any relationship at all, a neural network has the mathematical capacity to learn it. And that mind-blowing capability pushes us right along the timeline of AI evolution. I mean, we started at reactive machines, which just react to inputs with absolutely no memory. Today's massive generative AI models, they sit right at stage 2, limited memory. They use past data to inform present decisions. But the final 2 stages, theory of mind, where AI actually understands human emotions, and self-awareness, where the AI literally realizes its own existence, those don't even exist yet. Which brings us right to the edge of tomorrow. Think about it. If a simple neural network with just a single hidden layer can theoretically map any continuous function in the universe, what on earth happens when we give it a mind of its own? I'm going to leave you with that thought. Keep learning, keep questioning, and thank you so much for joining me for this explainer.